Right. This is joint work with my friend and co-author Akaki Mamagashvili from ETH Zurich. I'm Christoph from London. So this is an auction paper. What's the story? So there's this kind of very popular way of implementing, quote unquote, a sealed bid auction on a public blockchain where you basically go through some kind of commit and reveal scheme. So how it works in practice is you commit to a bid. There's a commitment phase. You want to commit to a bid by sending basically an encrypted version of the bid, some kind of hash you can think of. And on top of that, to cover your bid, you basically send a deposit transaction. And that deposit transaction very often is in public, right? So the bid is sealed, the deposit transaction is public. What is a deposit? Deposit should cover your entire bid, right? So that is the point of the deposit, so that you basically don't spam the auction, right? So you send a bid to the auction, and afterwards you cannot really honor your bid. So that's the purpose of that, right? And then, well, reveal phase, and you can then basically decrypt your bid, and then we determine who is winning the auction. And if you want to do a second price auction, for example, highest bidder wins and pays the second highest bid, right? Okay. So the issue is we want to analyze sort of this information leakage from a game theoretic point of view where we see the deposit transaction, right? So we have information on the deposit transaction, and that reveals some information about basically a willingness to pay in that auction. And that is information, and always if there's information, right, then you presumably other bidders will react to that information. Okay, that's the story. Just to prove that I didn't make that up, right? So there's one example. There are many of those auctions. One example is this webpage namebase.io, which is nice because it has a lot of nice data, sort of in a nice format. You can think of it as something similar as Ethereum name services, if you know that. So you bid on some kind of domain, and well, you have exactly this kind of auction format that I described to you to bid on those domains. Bids could be substantial. As usual, the most expensive item on this namebase.io is .nft. The domain goes to up to $84,000 US in value for this particular domain name. That is, I think, the record. So it can be substantial, but what you then observe in these kind of auctions is some kind of interesting strategic behavior around this depositing channel. So over-depositing and entry deterrent strategies, this is something that we're interested in. Let me just illustrate this with, as I said, there's nice data on that web page. So what you have, this is people bidding on .scholar, okay? And so there are a bunch of bids. Let me explain this picture to you. So there's the actual bid, the native token, you don't need to know it. It's called handshake for whatever reason. Those are the bold ones. Those are the bids. And then there's an additional amount on top of that. That's what they call a blind. And so that's after the basically auction, the bids are revealed. But what you only observe if you bid in this auction, you observe until the point in time, if you enter the auction, you basically observe this lockup amount, this deposit here, okay? And what is happening in this auction, that's why we've picked it, but this is sort of consistent behavior across many kinds of words. Domains is that you have this last bidder here, bidder 6, entering the auction, putting a very substantial deposit, right? And then afterwards the auction continues, but nobody enters anymore. And on top of that, he's certainly depositing much more than he's actually bidding, right? So he's bidding 101, whatever handshake tokens, that's roughly $30 or something like that. But he's locking up a deposit of 700, right?
Sorry, quick question.
Yeah?
Is the identity of the bidder known?
No. So in principle, this could be the same person. I don't know why he would do that, but in principle, yes. Yeah. Okay. So we have this kind of over-depositing in the 6 bid at least, right? And a much larger deposit than the actual bid, and some kind of entry deterrence, right? Of course, I mean, We don't know whether there were actually additional bidders who would have entered the auction but didn't, right? We don't observe of equilibrium behavior, but it's sort of a convincing story. And so no further bid is made, so there's this deterrence to a huge deposit transaction, right? So what do? We want to rationalize that in a sort of neat, stylized game theoretic model. It's some kind of signaling model, so bidders can signal something about their willingness to pay through the deposit transaction, right? And then we have this usual problem. I don't know if you know about signaling models. You have many equilibria in signaling, right? Because essentially you send a signal and somebody has to interpret it, and that somebody can interpret it in many different ways. But we can create this kind of equilibria, all kinds of equilibria separation where your willingness to bid is revealed, but also pooling kind of equilibria. And generically, you can create costly over-depositing. So people over-deposit much more than they need to honor the bid. And you have, often you don't allocate the item efficiently because of this kind of entry deterrence strategies, okay? That's the idea. Okay, as I said, very stylized model. So 2 bidders, 1 item, the simplest model you can think of. Valuations are identically distributed according to some distribution with compact support. A bidder makes a bid and a deposit. Deposits are costly, that's the important thing, otherwise you cannot get this kind of equilibrium, right? And we assume sort of the simplest setup where we have just a constant marginal cost of depositing, which can come through multiple channels. For example, you can think of volatility of this token in which you deposit. Right, you have to, in this auction that I've shown you, you have to basically place it there for 5 to 10 days, right? And it moves around quite a lot. The value of that might be bad, and it provides an opportunity cost. You can think of transaction costs. I think there are multiple reasons why it would be costly to put a large deposit, right? Or you can think of borrowing the token to make the deposit.
Sorry to be pedantic about it and interrupt on the same question again.
Yeah.
Do the 2 bidders know there are exactly 2 bidders in the setting? Because then it's sort of pseudonymous. Like I know there's only one other person bidding again.
Yes, in my stylized model exactly. Yes, they know that.
So they know that. Okay.
Yes, because otherwise, well,
It's not
too
2
complicated.
bidders in a group of maybe 100, but there are only 2 active people.
We know that there are exactly 2 bidders, right? So that is the point, because otherwise I cannot write down a model that would replicate this thing in equilibrium. But yeah, in reality, no. Okay? Second price auction we're studying just because it's sort of benchmark, right? And otherwise, if you have other kind of pricing rules, you have additional strategic interactions to the bid that we want to eliminate. That's why we have second price auction here, okay? So whoever wins of the 2 bidders, whoever places a higher bid wins the object and has to pay the bid of the other person, right? And if you lose the auction, then you have just to basically pay your depositing cost. Okay, 2 versions of the model. Very quickly, let me show you the benchmark is sort of if you could simultaneously bid, if you could hide the deposit, right, then you basically can just do standard auction stuff and you sort of get a reasonable equilibrium. And then the second thing is the more interesting thing where we have sequential bidding. This is sort of deterministic, again, not realistic, but otherwise, again, the model becomes too complicated. If we have the first bidder sort of entering first, and we know that, and then the second bidder reacts to that, right? So it's a signaling model. Bidder 1 sends a deposit transaction, signals something to bidder 2. Bidder 2 reacts. Okay. Okay, benchmark is just standard auction 101. I don't know if you know about auctions, but basically you can always characterize symmetric equilibria by some differential equation that determines your bidding strategy. And that's not too different from what you would observe in a standard second price auction. So what you get in terms of, this is your bid as a function of your valuation for the item, right? And basically what you observe is some kind of bid shading in the beginning, just because there's a cost of depositing, but other than that, there's nothing interesting happening in that case. So let me go to the more interesting case, which is a sequential bidding case. And as I said, so that we've cooked up this model in a signaling game kind of way, where we have one bidder bidding or depositing and the other bidder reacting to that. We need a tie-breaking rule now. In case of equal bids, the second bidder wins. Otherwise, existence could be a problem of equilibrium. Okay? And then it very much depends, of course, on the shape of the distribution, right, of the valuations, right? And intuitively, you can think of the situation where there's a high likelihood that the item is valuable to both bidders, or you could have sort of uniform, it's equally likely every possible value, or you could have something where low valuations are much more likely. But I think the high valuation case is presumably the most interesting. So let me go through the logic of that. So high likelihood of high valuation we model by just a convex distribution, right? Higher types are more likely. And so let us reason about equilibrium. In case of separation, right? What do I mean by separation? The first bidder sends different deposits for different valuations, right? So he observes his own valuation for the item, and depending on that valuation, he sends a different deposit transaction. Okay. In that case, the other bidder can perfectly infer the valuation of the first bidder just by observing the deposit, right? And then he can either match that bid that the first bidder made or doesn't bid at all. That's separation. And then what you would observe is that the first bidder does not enter the auction if he has a low valuation. Doesn't pay off because he has to basically send a costly signal through the deposit. He has to deposit a lot to show that he actually has high willingness to bid. That doesn't pay off for him. But we have this kind of equilibrium with separation conditional on entry. So low valuation bidder doesn't bother to enter because he has to deposit a lot, but the higher types, they need, they basically separate themselves. They put different deposit transactions conditional on entering. There's a proposition, but let me show you basically how those equilibria look like, right? So yellow curve is bid, okay? So you just bid your type. You don't enter, or you bid your type, right? Because it's second price auction. And the blue curve, that is your deposit, and you observe consistently this over depositing, right? So you deposit much more than you actually bid, and what is the function of that? It's just to signal something about your willingness to pay, right? And so you have costly over depositing equilibrium. Okay. That's bad in the sense that we have loss in terms of costly over depositing, so costly signaling. But also, if both bidders have low valuations, then we might allocate the item wrongly, so to speak, to the low valuation bidder. Okay. And you can do that in much more generality. But let me show you instead sort of this pooling equilibrium, which really is an equilibrium that sort of tries to mimic this stylized fact that we observed about the auction, where you have basically entry deterrence. And in these kind of equilibria, basically, you have just two deposit levels, right? So either you choose to not enter the auction, or if you choose to enter the auction, you put a huge deposit. And everybody does that. And then you have this kind of equilibria where basically you have two depositing level, low, high, and you have, again, just choose for bidding, right? That's how the second bidder reacts to. So he basically doesn't enter the auction because if he observes a high deposit level, he's deterred from entering the auction. He doesn't bother to bid unless his type is very high, right? Exactly, this is this kind of entry deterrence strategies. Okay. And that is even worse in the previous equilibrium, just for the fact that you now have very often the case that the item doesn't go to the highest willingness to pay bidder, right? So you have a problem of allocative inefficiency, and you have costly over depositing as before. Okay. Let me wrap up. So what did we do, or what we were trying to do? We were trying to create a stylized model of costly signaling in these kind of auctions. So we take the auction format as given, right? Exists, used a lot. And we try to make the point that if you have this additional channel of information leakage through the deposit transaction, fundamentally changes the strategic structure of the auction. You observe it sort of stylizedly in the data, but you certainly can reproduce it as an equilibrium model. We have this kind of entry deterrence strategies in equilibrium, which makes the auction very inefficient, right? And that's bad, okay? That's the point. And that's all.